All right, let's try a little bit tougher one. Each problem kind of gets a little bit tougher because we're making our brains tough and smart. Example 5. A 1,500 kilogram car drives east at a speed of 30 meters per second before seeing a deer and skidding to a stop. If the coefficient or mu k of kinetic friction is zero point 0.8 for rubber sliding on pavement, calculate the stopping distance for the car. All right, so it's a forces problem. Whenever you have a forces problem, you're always going to use the 5 steps for success. So go ahead and hit pause here, try it out for yourself, and then when you want to check your answer, hit play. All right, so in this case, again, it looks like just a box on a table, but in this case, it's a car that's driving east, which we kind of said east would be to the right. So step number 1, I'll put right here. Step number 1, draw an FBD. So the force that always acts down is weight. Even if it's a car driving, you always have a weight force going down. The car is touching the road. So we have our normal force going up and our weight force going down, and that's all we have in the y direction. And then in this case, it says sees a deer and skids to a stop. So when you see this word skid, that's basically telling you that it's got sliding friction, or the force of kinetic friction that's going to slow it down. It's kind of like as a kid when you locked your brakes on your bike and you could see that you left a little like rubber trail on the sidewalk, okay? So that's what's stopping this car. And the car was going east, so that would be right in our picture, which means that the force of friction, or F sub k, is going back. So force of friction always acts against your motion, so it's going to be going that way. And then again, it doesn't say anything about any other force. We don't have a force that's pushing the car forward at this point because they're braking. So basically, the only force acting in the x direction is the force of the kinetic friction, Fk. All right, so keeping track. Step number 1 is done. We did our FBD. Step 2 says define your coordinate system, which again, we're just going to go traditional. The car was going to the right or east, so there's our traditional coordinates. And then step 3 says do SOHCAHTOA and any vector that's not aligned with x or y. This picture looks exactly like the pictures we've been seeing where you have the vectors going up or down or side to side. So no SOHCAHTOA. We'll save that for the next example. And then number 4 says add your forces in the x and y direction. So I'm actually going to color code them this time. We're going to go ahead and we're going to add our forces in the x direction. And if we look, the only force that we see in the x direction from our FBD is Fk. And the thing that's special about Fk, it's going to be a negative force because it's going to the left. And we've defined to the left as negative. So we said that's equal to max. And now I'm just going to start to get in a little bit of a habit, is that it's nice to have acceleration. So I'm going to kind of preemptively solve this for acceleration. Just because we realized by doing these problems, it's nice to get your step 4 equations and then use those to get your acceleration. So you can see I'm going to say acceleration is going to be equal to negative Fk over m. And then I'm just going to circle this one, saying this is kind of a nice handy equation to have. All right, now let's sum our forces in the y. And again, we have the same thing we've gotten every time we've done these problems. N minus w equals may. There's no acceleration in the y direction, so that means that n is equal to w, which is equal to mg. So there's another equation that's nice to have just in our back pocket. All right, step 4 is complete. Step 5 says use your physics format, the give and want, and now we actually get to solve what's going on here. So we look back at our highlighted information from example 5, and we have our mass, it's 1,500 kilograms. We have it's driving east at 30 meters per second, and they're going to skid to a stop. So that means that 30 meters per second is your initial velocity of 30 meters per second. And if you're coming to a stop, the whole goal behind that is that your final velocity is 0, because that's the definition of stopping. And then they tell us mu k is equal to 0.8. And don't worry, that doesn't have any units because it's just a coefficient. It's not a force, it's just a coefficient. And then I think that's all the givens we got for right now, all the ones we have. And then for want in this case, it says calculate the stopping distance. Here, Lucy barking in the background. For this one, it says calculate the stopping distance of the car. So stopping distance, the car is traveling side to side. So they're asking you to get your change in position or your displacement, delta x. So we go equation shopping, and we need an equation that has a delta x in it. We also need it to have a VO and a V. And the one thing about it, it does not have time. So they don't give us time as a given. So you might remember back, we seem to use this one a lot when we don't have time. V squared equals VO squared plus 2a delta x. That's the one that we use when we don't have time. So we're going to solve this bad boy for delta x. So it's going to be v squared minus VO squared equals 2a delta x. And then divide both sides by 2a. So we're going to get our equation delta x equals b squared minus VO squared over 2a. And we look and we're like, oh, for our givens, we have v, yep. We have VO, yep. Oh, a, we don't have a. So we're like, okay, it'd be nice to be able to get our acceleration of our vehicle, of our car. So we're going to come back up here and look at this equation. And we actually do have an equation to get a. So I'm going to do like a little side venture down here. Ax is equal to negative fk over m. And we know what m is, 1,500 kilograms. We don't know fk. And some people are going to be like, yeah, Mr. We know fk. It's right here. It says mu k equals 0.8. But I just want to remind you, this mu k, that's not the same thing as fk. That's the coefficient, and this right here, fk, is the force. So we're going to have to think back to our warm-up that we did at the very start of these videos. Fk is equal to mu k times n. So I'm just going to substitute that in there. So basically all I did is I said Fk is equal to mu k times n. And then you're like, oh, but we don't know what n is. That's not one of our givens. But we do know we have this equation, n equals mg. So all I'm going to do is I'm going to say, okay, well, let's substitute in mu k instead of times n. We're going to say n is equal to mg. That's still over m from before. And that's nice because you have an m on top, you have an m on bottom, so they're gone. So our equation, now it's a little arrow there, a sub x is going to be equal to negative mu k times g. So we basically simplified down an equation for our acceleration is just equal to mu k times g. Which is negative 0.8 times 9.81 meters per second squared. So let's go ahead and crunch it. We'll say, what's 0.8? 0.8 times 9.81 is going to be 7.8. So our acceleration for this problem, a in the x direction, is going to be negative 7.848 meters per second squared. So there's our acceleration. And now we can use that acceleration, and we're going to plug it in for our a right there. So I'm kind of off the page here, but let's see if I can squeeze this last line in here. So if I say delta x is equal to v squared, which is 0 squared minus VO squared, which is 30 meters per second squared, all over 2 times negative 7.848 meters per second squared. Sorry, kind of getting run out of room here. So if we do that and you crunch them, I got that worked out to be 57.34 meters. So that's how far the car would skid before it comes to a stop. And you might ask yourself, wow, that's a lot of work. When would you ever need something like this? Well, it's actually, I was reading this magazine called Consumer Reports, which talks about the cars that are best stopping in different conditions. And when I went to buy tires, they actually have all these rankings. They just call it stopping distance for a particular set of tires. So actually, material scientists and engineers, it's actually, they rank their tires for how good they are at stopping a car based on what their delta X values are for that tire. So you wouldn't want to buy a tire that had a really huge stopping distance, because the whole goal is to stop you and stop you quick. So it's actually a pretty practical calculation we just did here. Every tire is rated by their stopping distance to see if it's a good or bad tire. So I like this problem because I actually just was looking up information about this to buy new tires for my car. All right, we'll stop there. Thanks for playing along, and go Physics All-Stars.